This is sort of the other side of the story of climate change. And we call ocean acidification. If you think that carbon dioxide is the main driver for climate change, this is the other half of the story, is the impacts on our ocean ecosystems, and this is what I'll be talking about today. So what I want to talk about is what is ocean acidification, why our coastal areas on the West Coast are particularly vulnerable to ocean acidification, and I will talk a little bit about some of the IPCC efforts and other efforts to look at future impacts. Now, as we all know, mankind has been burning fossil fuels for energy, coal, oil, natural gas. And since the beginning of the Industrial Revolution, we've released about 2 trillion tons of carbon dioxide in the atmosphere. And the oceans absorb about 28% of that. It says 25 on the slide, but the latest calculations now, it's about 28% of that. And it does so very slowly. It takes it up fairly slowly. Most of that carbon dioxide is still up in the upper part of the ocean, upper 500 meters of the ocean, because of the slow circulation. And carbon dioxide is an acid gas. It reacts with water to form carbonic acid. And then that carbonic acid completely dissociates. It forms a hydrogen ion and a bicarbonate. And in doing so, it reduces the pH of seawater. Since the beginning of the Industrial Revolution, that pH change has been about 0.1 pH units, which is a 30% rise in the hydrogen ion concentration, a 30% rise in acidity of the surface ocean since the beginning. Our sister laboratory in Boulder, the Earth System Research Labs, monitors the global atmospheric monitoring system, and these are the 67 stations throughout the world. They send samples to the Boulder laboratory, and so we have a very good and long-term record of atmospheric concentrations. I want to give you this is the zonal mean average of CO2 in the atmosphere starting from January 1996. We're going to show you a 10-year record. This is the South Pole, and this is the North Pole. And what I want you to see is the changes that take place over time. If we can start the movie. You can see that with the uptake of carbon dioxide in the summertime, the northern hemisphere draws down. It's released during the respiration in the wintertime. But just from your eye alone in this 10-year record, we can see the entire record of atmospheric CO2 increases. In this decade, it increases at about 2 parts per million. And it's increasing faster than the previous decade because we're increasing the rate of release of CO2 in the atmosphere still about 3% per year. So we haven't slowed things down. We're actually increasing the rate. And you can see that in these very detailed records. For the oceans, we have been monitoring the oceans since about 1989 or so. And this is the Mauna Loa record. That's the record that Dr. Charles Keeling started in 1957. I'm just showing you part of the record. The NOAA Earth System Research Laboratory has taken over that responsibility. And the blue here is the same record for the oceans, in the oceans. And you can see that the trend of increasing CO2 in the atmosphere is mimicked by the trend of CO2 in the surface oceans. The oceans are taking up that carbon dioxide, and so they increase at the same rate as the atmosphere. This is one of the reasons why we know that this is occurring. And when you then calculate the pH change of the surface waters from these observations alone, we can see the acidification taking place. This is 0.02 pH unit change per decade. Now we have several time series sites around the world, and we get very similar records wherever we go. So from observations, we know that we are acidifying the oceans. Very, very clear. The chemistry of this is very clear. So what is the chemistry? Well, as I said, it's very thing. You learned all this in high school. You may not remember it, but you'll learn it in high school. CO2 reacts with water to form carbonic acid. Carbonic acid. This is the same thing that's in your pop. When you're drinking pop, that's the CO2 you're looking at. It releases a hydrogen ion. This gives us our acidity. That hydrogen ion, most of it reacts with carbonate to produce bicarbonate, which means we're reducing the carbonate ion. That's going down. The acidity is going up and the carbonate is going down. And so then the net reaction is CO2 plus carbonate to form bicarbonate. So what is the overall impact? We can see that from the pre-industrial, the pH of seawater, which is a logarithmic scale, has decreased about 0.1 pH unit. That's a 30% increase in the hydrogen ion concentration. And the carbonate ion has decreased 16%. By the end of the century, the pH will decrease another 0.3 or 0.4 pH units using the IPCC CO2 emission scenarios. That's 100 to 150% increase in the hydrogen ion concentration. Now we're talking about major changes in chemistry of the oceans. pH is, hydrogen ion concentration and pH are master variables. They affect the chemistry of many, many chemicals and compounds in seawater. So this is a very important change. And that carbonate ion concentration is now decreased by 50%. Now the organisms that produce shells and skeletons right over here having a hard time because they can't get enough carbonate to produce their shell or skeleton. So what we know for sure is that about 28% of the CO2 generated by human beings since the mid-1970s has been absorbed by the oceans. Ocean acidity has increased 30% since the pre-industrial age. Ocean acidity is projected to increase 100 to 150% by the end of this century. And the current acidification rate is at least 10 times faster than anything we've seen over the last million years or so, and maybe as much as the last 50 million years. Now, one of the most important statements that you will hear by the deniers is that the oceans will never become acidic, so calling ocean acidification is alarmist. This is false. The reason why it's false is that acidification is the process of lowering the pH, not the end state. It's the direction we're going. Your body has a pH of about 7.45. It's basic. If your body changes its pH towards acidic conditions from 7.45, 0.2 pH units to 7.25, you will go into coma. That's how much your blood system is dependent on the pH. That disease is called acidosis. Still basic, but it's called acidosis. This is where these terms come from. It's linked in medical science, and it's linked in our society of science. Same way you think about it is if you lived in Minnesota like I did, and it was 40 below, and it got 10 below, you'd say it's warming. You really would notice the difference. This is the same point. We're down here at a pH, we're moving in the direction towards neutral conditions. The organisms have evolved at a pH of 8.2. Any changes to that, they're significantly impacted. The other issue that's just as important is that we're changing the CO2 concentration in the atmosphere and therefore the ocean at a rate that is anywhere from 10 to 100 times faster than anything they've seen through most of their life cycle and most through their generations where they existed. They have to learn to adapt to these very rapid changes that are taking place, or they may simply die off. And you can look in the geologic record and see where they have died off under similar conditions. The major chemistry that you need to understand is that we as chemists have an indicator of whether it's favorable for producing the calcium carbonate shells or skeletons. This is calcium plus carbonate to form calcium carbonate shells and skeletons. Things that make oyster shells and clams and oysters and lobsters. This is the reaction that takes place. And if it's favorable for reaction, the saturation state, which is that calcium times the carbonate divided by the parent solubility product, that saturation state should be 1 or above. And 1 or above, it's favorable for production of that shell. If it's less than 1, the shell will begin to dissolve. I call that being corrosive because you actually see the shells dissolving in pitting. So really what's important is where this occurs in the ocean and what we might expect. High numbers are good. 4 or 5 is good for production of shells. When you get close to 1, the slowdown of the process is very dramatic, and somewhere near 1, dissolution will take place. The common carbonate minerals are aragonite, which are pteropods and corals, and calcite, which are things like forams and coccolithophorids. So what we have done throughout the U.S. is to develop an observing system this is the global observing system that's just been developed and now is been approved as of this summer, called GOAN. And what we do is we put out moorings and we take cruises and have stations where we collect chemistry data and physical data. This is one of our moorings right here. We're actually measuring the PCO2 and pH of water and monitoring the changes in real time. And when you do that, you can determine how much of the anthropogenic CO2, the man-made CO2, is in the water column. We published this in Science in 2004, and you can see all the anthropogenic CO2 is up where animals live. It's still up in the upper 500 meters. That's because the slow circulation of the ocean, from the surface ocean to the bottom, around the circuit from the Atlantic to the Indian to Pacific, and back up to the North Pacific. So that takes about 1,500 years. So we're still in this regime where most of it's in the upper part of the water column, affecting the organisms. And so what we can do then is to calculate where this equilibrium state, where the waters become corrosive, is equal to 1 or less and dissolution take place. And it turns out that in where we live on the West Coast, this is really close to the surface. It's less than 200 meters most places. And in Alaska, it's less than 100 meters. It's much more corrosive in high latitudes than it is at low latitudes. And the reason is CO2 goes into the ocean at lower temperatures. The higher latitudes, more CO2 goes in the ocean, faster rate of acidification takes place. Our colleagues have done models to project what the saturation state of seawater will have if we stop CO2 emissions right now, if we have CO2 emissions at 550, or if we do a business as usual scenario of 800 parts per million. For the different regions in the ocean, the tropical ocean, Southern Ocean, and you can see in the Arctic Ocean and Southern Ocean where there's more carbon dioxide going in, we're going to hit this tipping point of equilibrium of saturation state less than 1 fairly quickly. For the Arctic oceans, about 2030. For the Antarctic oceans, about 2040 or 2050. We're coming up against a tipping point where the entire water column will become undersaturated fairly quickly. These are the relative pH changes for these types of scenarios. So it makes a big difference what CO2 emission scenarios we follow as human beings, what the tremendous impact that will have on the chemistry of the oceans. That's the major take-home message that I want to make sure everybody understands. These are very striking differences in terms of chemistry of the oceans. Now this is a movie that was developed by Scott Doney and Sarah Cooley at Woods Hole using the NCAR model. This is the pre-industrial condition for saturation state in surface waters. Remember I said 4 or 5 is good, so all the blues are good. Or less than 1 means red, so we don't have much in the way of red yet, but you can see the higher latitudes are very vulnerable. This starts at 1880. We'll run that movie right now. And watch the changes that go into the future. You can see we already have started making changes to the chemistry of the ocean, and we see significant changes by the year 2000, which we reach right now. But going out to the end of the century in a business as usual scenario, you can see the entire Arctic Ocean becomes fully undersaturated, the North Atlantic and the North Pacific undersaturated, entire Antarctic Ocean undersaturated. And in the tropical regions, such a large change in saturation state that the coral reefs would begin to slow down their calcification, forming their structures by as much as 30 to 60% by the end of the century. This means they can't keep growing fast enough to keep up with sea level rise. So that presents a major problem for the corals. This is a very, very dramatic response to the entire chemistry of the oceans. In our coastal region along the Pacific Northwest, we have an additional vulnerability that combines with the anthropogenic CO2 to affect the chemistry of seawater. And this is because in the Pacific Northwest region, the winds shift. In the wintertime, the winds are from the south. There's there's downwelling conditions, everything is fine. But in the spring, about April or so, the winds shift, they come from the northwest. And there's a natural process of when the winds come from the northwest, that pushes the surface waters offshore, and it draws the bottom waters, which are already enriched in CO2, as well as enriched in anthropogenic CO2, along the bottom all the way to the beach. And then it gets pushed out in that surface waters from the beach, so it goes all the way. So it's coming along the bottom. It's picking up that anthropogenic CO2. It's enriching in CO2 with time, and that corrosive water then is much more corrosive than what we would normally get in the open ocean. That water has a pH of about 7.8, 7.7, and it's getting to our beaches right now. This is the reason why we have this. The combined impact of anthropogenic CO2 in this upwell waters makes our waters along our coast very, very corrosive. The anthropogenic CO2 is penetrated down to 500 meters. This upwelling is from about 120 to 130 meters. It already is building up as anthropogenic CO2 with time. So as that water is coming onto the continental shelf and being upwelled, it's always picking up more and more anthropogenic CO2 along the way. And so we see the combined impacts. In the pre-industrial area, we had this upwelling of low pH water, but it didn't go, in most cases, it did not go below that corrosive layer. It was the saturation state, less than 10% of the water was undersaturated. Right now, 30% of the water is undersaturated in this upwelled water because of the acidification from anthropogenic CO2. So this, here it is. It comes along the bottom like this. It goes all the way beach, then comes outward from that word out, affecting the organisms in the water column. This next model is going to show you that process. So watch the blues. The pH are the low pHs along the blues. It starts on day 3, which is January. It's going to go through the year. You can watch when you get to about 90 and see what happens. Watch the blues along our coast. And okay, run the model. Nothing until about day 90. Then all of a sudden the upwelling begins. You see here it goes along our coast. This is Oregon. This is Southern California. Entire coastal system is impacted from April all the way to November. Okay? So this is when they're impacted by this. This is what we go out and monitor every day. So what we do is we have experiments that Shalin does in laboratories. We have mesocosm experiments that go out in the field. We control the CO2 level. We can do this aboard ship. We have similar mesocosm experiments aboard ships. Many, many ways to do it. We have large-scale mesocosm like at Biosphere 2. And what we're looking at is not just acidification alone, but here's the impacts of acidification. CO2 goes up, bicarbonate goes up, carbonate goes down, pH goes down. There are other impacts that we have to think about because of climate change as well. Increasing temperature, decreasing oxygen. All these are climate change impacts. From an ecosystem perspective, it's the combined impacts of the increasing temperature, decreasing oxygen, and acidification is what the organisms are seeing. In addition to that, there's other forms of pollution that we have to take in consideration, all changing the physiology and chemistry of the organisms. So it's our job to parse out each individual impact and the combined impacts. That's what we're doing in the laboratories. So the challenge to the marine sciences is what all these multiple stresses do to the ecosystem. We talked about decreasing calcification rates. It's very important to understand that pH changes affects nutrient speciation, trace mineral speciation. A trace mineral can be very toxic in low pH conditions and not so toxic in high pH conditions. That's affected. Shifts in phytoplankton diversity, reduction in growth, production, lifespans. In most cases, the juveniles are more sensitive than the adults, so you got to look at different stages. The reduced tolerance to environmental factors, and some of the studies have been showing that at high temperatures and high CO2, the organism is more strongly impacted. This is true for corals, for example. Changes to species biogeography, biogeochemical cycles. The latest one is behavior patterns of organisms. Some organisms are just affected in their behavior patterns, which affects their survival. All these things have been recently studied. Lastly, I'll just say is that, These things are important because we eat shellfish, we eat seafood, so the impacts on shellfish impact humans. But they also impact the ecosystem and the organisms because, you know what, fish eat shellfish too. And so they're dependent on the food chain and how they work. And the classic case of this, the most clear example on our West Coast, is the great shellfish crises of 2006, 2007, in which the hatcheries were no longer able to make their oyster seed because they didn't realize at the time that an acidification was taking place. That acidified waters were getting into the tanks and killing the oyster larvae within 2 days. And this was having a huge impact on the oyster industry. Thank you, we had Maria Cantwell. She was able to work with the scientists to get some money during the stimulus package time so that scientists could put the pH sensors right in the tanks themselves, monitor the pH, develop an adaptation strategy that worked. And within 2 years' time, we developed an adaptation strategy that saved that entire industry, 3,200 jobs, about a $110 million oyster industry was saved in that process. And this is the reason why. It's very simple. In the life cycle of an oyster, in their very earliest stage, when they just hatch, they have an egg yolk. That provides the energy for their survival. And their survival is dependent on producing their shell in those first few days. If they don't produce their shell, they die. And this was what was happening in the tanks. They couldn't, pH was so low, they couldn't produce the shell. This is the work that we did right in the hatchery itself. And this showed at this saturation state right here, they were no longer producing any organisms. And so therefore, this was the first tipping point for ocean acidification that's completely documented in an oyster hatchery. And so we now know that there are clear, rational reasons why this is occurring with our ocean industry. We developed an adaptation strategy. Within 1 year's time, they saved that industry $35 million by their calculations alone. So scientists working with federal agents, working with the industry, saved the industry. And this is an example of how important ocean acidification is to us from an economic perspective. U.S. 8 federal agencies are working together. We have an interagency working group. We monitor the process. We're developing the ecosystem studies. We're doing the modeling work. We're developing adaptation strategies, and we're trying to do an education outreach to let everyone like you know what we're doing. These agencies are now working at the international level through the International Coordination Center in Monaco, just established, mostly supported by our State Department, to develop an international research effort on ocean acidification. I will stop there.